Hello, my name is Victor Heng Jun Hong. My matrix number is 25004013/1, and this is the video presentation for the course KIB1016 Electronic Devices. In this presentation, I will be talking about the application of BJT or bipolar junction transistor in hearing aids. Before I talk about the BJT, I want to first give a quick explanation of the biomedical device in question, the hearing aids. The hearing aids is a device that can allow people with hearing problem pick up sounds that they normally could not hear by amplifying the incoming sounds in their surrounding. The hearing aids does this by picking up sounds from the surrounding using a built-in microphone, turn it into electrical signal so that it can adjust the sound electronically by using the amplifier circuits in it, and project the sound through the receiver that is planted nearer to the person's eardrum. When it comes to hearing aids, many different types have used different components to act as a signal amplifier. Some of them use the FETs, some use the op amps, but the main focus of this presentation is the BJTs. Of course, which means that the hearing aids being referred to in this presentation is the analog hearing aids, as the digital hearing aids does not rely on transistor as its main component. Although most modern hearing aids are digital, but I think it is important to look back to the older model and the importance of BJT as a signal amplifier. The BJT is commonly used as an amplifier due to its nature. A small increase in the base current, IB, will cause a huge increase in the collector current, IC. Through the formula IC equals beta times IB, with beta being the current gain. Because of this, it is very effective at being an amplifier, which means that using it in a hearing aid is ideal, as the whole point of the device is to amplify sounds that the user's own ear can no longer pick up naturally. This is the block diagram of the amplifier circuits in most hearing aids. As you can see, it has multiple stages of amplifier, and the results of the sound waves are displayed below. The first stage is the pre-amplifier. The electrical signal from the microphone is too weak to directly process, so it needs to be amplified first by this first stage of amplifier, as it provides a substantial voltage gain. The second stage is the voltage amplifier. Although it is not shown here, it provides most of the hearing aid's gain, as it raises the signal to a suitable level for the output stage. The third stage is the tone control. It boosts higher frequency and attenuates the lower one, filtering the sound for the output. The fourth stage is the output amplifier. It greatly increases the current capability so that it can allow the receiver to produce a clearer sound. This is what the amplifier circuit of an average hearing aid looks like. It is a 3-transistor audio amplifier circuit that is capable of the function I mentioned in the last part, taking a small signal and amplify it to drive the receiver/earphone piece. In the next few slides, I'll explain in detail as to what each of the components in this circuit does. The first part is the input stage of the circuit. The microphone acts as a signal generator of this circuit, producing a small AC voltage signal. The 10K ohm resistor to the top left supplies DC bias current to the microphone. The coupling capacitor, the capacitor in the middle, prevents microphone's DC bias to mess with the transistor's bias point. As for the 200K ohm and the 300K ohm resistors, form a bias network for the transistor in the picture. Both resistors establish the transistor's operating point so that it remains in the active region and keep the transistor ready to amplify both positive and negative signal from the input signal. The transistor itself acts as a signal amplifier as explained before, as a small increase in the base current causes a huge increase in the collector current. The 10 microfarad below the first BC547 transistor is an emitter bypass capacitor. It behaves like a short circuit and the AC signal bypasses the emitter resistor. It also significantly increased the gain. And this is the output stage. In the output stage, the BC557 is a PNP transistor that acts as a current amplifier that produces a stronger drive signal in accordance to the changes in the collector voltage of the first BC547 transistor. It also supplies the current to the output BC547 transistor. That same transistor is the one to drive the earphone piece, because the earphone piece requires a strong current to move and produce sound, so the output BC547 transistor is able to supply enough power to it. Then, the earphone piece converts the electrical signal back into sound wave. In this last part, you can see that a 10K ohm resistor is connected to the emitter of the first BC547 transistor, which is called a feedback loop, and the resistor itself is being referred to as a feedback resistor. It is able to control the gain and reduce the noise of the incoming signal. The 3.3 ohm resistor is located at the output of the emitter of the transistor, which can function as a current stabilizer because if the output current increases too much, the base emitter drive decreases and the current will be limited. And so this is the overall signal flow in the amplifier circuit from start to finish. Outside sound were picked up by the microphone, it converted into electrical signal, which then goes through the coupling capacitor and then enters the BC547 transistor. It acts as a voltage gain, and later it went into the BC557 transistor, which acts as a current amplifier. Since the formula of power is described as power equals to voltage times current, the second BC547 transistor acts as a power amplifier which goes to the earphone piece. The earphone piece, or the receiver, converts the electrical signal back to sound waves, which will now amplify, and that is the end result that will be heard by the user of the hearing aid. And that is the end of this video presentation. Thank you for watching, and the references for this presentation is available in the next slide.